Today I will be presenting the work we did with Simon Patry and Benoit Valleron on optimizing hybrid quantum classical circuits. We represent these hybrid quantum operations with diagrams where we have classical and quantum wires. We also have some pure quantum gates and a set of operations interacting with the classical environment. The usual way of optimizing this kind of circuits is by finding patterns that we can rewrite into smaller ones. The problem with that is that there is no complete set of patterns, so we can always find bigger and more complex ones that we want to rewrite. We can sidestep this problem entirely by using the ZX calculus. This is a formal graphical language where we represent quantum operations using diagrams. These are graphs with a set of inputs and outputs and two kinds of color nodes. We have green nodes or Z spiders and red nodes. They also have some phase as a label. There is also an operator representing the Hadamard operation. For simplicity, we will replace it with a special kind of wire or edge we call a Hadamard wire. Here, these derive spiders are just identities. The ZX calculus comes with a complete set of rewrite rules. Between them, we have the fusion rule that let us merge spiders of the same color connected by regular wires. We also have another rule that let us change the color or swap the colors of spiders by adding some Hadamard wires to its connection. Although this may seem like it adds a bit of complexity to the diagram, it let us only work with a single kind of spider during optimization. Another point to note is that the diagram can be freely formed. We only care about the topology, so we can move all the spiders around without changing the interpretation of this diagram. Using this ZX calculus, Simon Patry with Duncan, Kissinger and Van der Wetting devised an optimization procedure called the Clifford optimization that works for pure quantum circuits. They start by taking a circuit, then translated it into a ZX diagram in a special graph-like form, then applying some specially crafted rewrite rules, and finally extracting it back into a circuit. We use this procedure as a base for hybrid quantum circuit optimization. The problem is that the ZX calculus only allows for pure quantum operations. So we have to use an extension called the ZX ground calculus. This extension adds a new information discarding operation that will let us represent measurement. Since this ground operator will be always connected to a spider, we will call all the construction a grounded spider. The calculus also defines a number of extra rewrite rules. Between them, we have the discarding one that deletes spiders connected to grounds, and another rule to disconnect grounded spiders connected via Hadamard wires. Using this ZX ground calculus, we can now define our translation from hybrid circuits into diagrams. For the circuits, we allow a restricted set of classical operations composed of nodes and XORs. Since we translate all the classical or quantum wires into regular ZX wires, we will also have to keep track of which of the inputs or outputs were classical and which were quantum. The resulting diagram of our translation is in a special form we call weakly graph-like. where we only have green spiders and, after applying some fusion rules, internal Hadamard wires. We then transform this diagram into a strict version where we separate the grounded spiders from the inputs and outputs. This will let us move them around internally so they can interact during the optimization. Once we have a strictly graph-like diagram, we can talk about its underlying structure in the way of an open graph. That is a simple graph where we have a set of input and output nodes. Here we mark the grounded spiders as outputs of the open graph because they represent some discarding of information into the environment. Now, when we translated our circuit into a diagram, we blur the distinction between the lines of the circuit, because now we can just move all the nodes around. But we can define a property on this open graph called a focused-gFlow that will give us some notion of dependency and time between the spiders. We will need this property when extracting the diagram back into a circuit. It is important that we preserve the gFlow property during all the optimization, so we must restrict which rewriting rules we apply. On the gFlow optimization, Duncan et al. Introduced a number of gFlow-preserving rules that delete spiders with a phase multiple of pi/2 on the diagrams. Here the dash boxes represent any number of connected spiders. They apply these two rules repeatedly and eliminate the spiders until they cannot find any more matches, and then terminating. We have adapted these two rules to the ZX ground calculus and also introduced a number of gFlow-preserving rules that interact with the grounded spiders. The first one of the rules is the discarding, that deletes any spider connected to a degree 1 grounded spider. We also have the ground polypivot, where we delete spiders with a phase of 0 or pi that are connected to a grounded spider. With these rules, we could apply the same strategy of finding any available matches and deleting spiders until we terminate. But there is a way to look for extra optimization opportunities by looking at the ground cut of the map, of the graph. The ground cut is a partition between the grounded spiders and the non-grounded spiders. We then can talk about the by-adjacency matrix of the diagram as the matrix that encodes the connectivity between these two partitions. We also introduced a new rule that will let us apply the row sum operation on this matrix via modifying the graph. So with this, we can now apply a Gauss elimination procedure to reduce this matrix to a reduced echelon form. After this, we may have in the resulting matrix some rows where all elements are 0. And that means that in the graph we have a grounded spider that's not connected to anything. So we can just delete it from the graph and we're done. We may also have some rows with a single non-zero element. That corresponds to grounded spiders of degree 1. So there we can apply our discarding rule. Now, with this we can define our optimization algorithm, where first we start by applying the pure gFlow optimization and then running the Gauss elimination process on the by-adjacency matrix, so that then we can look at the matrix to find matches for our discarding rule and deleting any isolated grounded spider. We can also then apply the ground poly pivot rule if applicable. We then can repeat this process from the Gauss elimination until we reach some local minima where we have a reduced diagram. And with that, we can then pass into the extraction of the circuit. For the extraction part, we modify the algorithm from the gFlow optimization. We use the similar strategy where we define a set of border spiders starting from the outputs, and then we sweep left by extracting one spider at a time. Our contribution comes from two special cases that were not present on the gFlow optimization. The first one is the fan-out, where we have a single unextracted spider that's connected to multiple spiders on the border. This can be interpreted as initializing some new qubit and then applying some Hadamard's and control sets. The other special case is the fan-in, where we have multiple unextracted spiders connected to a single spider on the border. Here, since we know the diagram has a gFlow, we can prove that at least n-1 of these unextracted spiders are grounded spiders. So we can extract them as a measurement on a qubit than just discarding the classical result. Then at the end of the extraction, we can look at the classical and quantum labels of the inputs and outputs and apply some qubit preparation or measurement where necessary. We can also apply some color change rule where applicable to reduce the number of Hadamard's. And with this, we reach a valid extracted circuit for our diagram. But if you look, we can see that all the internal operations are pure quantum. For example, here we are preparing a new qubit from a classical input to use it as a control for a knot and then just measuring it right away. To solve this problem, we introduced a new algorithm that detects wires of a circuit that carry classical data. With this, we can interpret and detect which part of the circuit we can implement classically. So in this case, we can see that this is just a NOT gate with a classical control. So in this talk, I describe an optimization procedure for hybrid quantum classical circuits using the PyZX ground calculus. We introduced a number of gFlow-preserving rules and extended an extraction algorithm to be able to extract this kind of diagrams. We also included a classicalization algorithm that detects part of a hybrid circuit that can be realized classically. We finally implemented all these algorithms in the PyZX Python library, where we were able to test and benchmark the results. So, thank you very much.